The National Electrical Code does not explicitly address the bonding of electrical metallic tubing or EMT sleeves that are protecting grounding electrode conductors. However, industry best practices recommend that all metallic raceways and enclosures containing grounding electrode conductors be bonded to the conductor at both ends. This ensures a continuous and reliable grounding path. Bonding the EMT sleeve to the grounding electrode conductor provides several benefits. Firstly, it improves the grounding path. This ensures a low impedance path for fault currents and lightning strikes. Secondly, bonding minimizes electrical noise induced in the grounding electrode conductor by adjacent circuits. Thirdly, it enhances safety. It provides an additional protective layer in the event of a ground fault. Based on industry best practices, it is recommended that a 24-inch electrical metallic tubing sleeve should be bonded to the grounding electrode conductor at both ends. This can be achieved using a bonding jumper connected to the sleeve and the grounding electrode conductor. In conclusion, while the National Electrical Code does not explicitly require bonding of electrical metallic tubing sleeves in this specific application, industry best practices strongly recommend it. Bonding the sleeve provides numerous benefits and ensures a safe and reliable grounding system. It is essential to understand the role of grounding electrode conductors in electrical systems. These conductors provide a crucial low impedance path for fault currents to return to the source, ensuring that protective devices like circuit breakers or fuses can quickly interrupt the circuit in the event of a fault. This rapid interruption minimizes the risk of electrical shock, fire, and equipment damage. Grounding electrode conductors connect the electrical system to the earth, typically through grounding electrodes such as ground rods, metal water pipes, or concrete encased electrodes, often referred to as UFERs. The size and type of grounding electrode conductor are determined by the size of the service entrance conductors, as specified in the National Electrical Code Table 250.66. The grounding electrode conductor must be appropriately sized to handle the maximum available fault current. When a grounding electrode conductor is run through a metallic raceway, such as electrical metallic tubing, there is a possibility of inductive reactance, which can impede the flow of fault current. This is because the alternating current flowing through the conductor creates a magnetic field that induces a voltage in the metallic raceway. If the raceway is not properly bonded, this induced voltage can create a circulating current, which opposes the flow of fault current and increases the impedance of the grounding path. By bonding the electrical metallic tubing sleeve to the grounding electrode conductor at both ends, you effectively create a parallel path for fault current. This parallel path reduces the overall impedance of the grounding system and ensures a more effective path for fault current to flow back to the source. This is particularly important in situations where high fault currents are possible, as it helps to minimize voltage rise on grounded metal parts and reduces the risk of electrical shock. In National Electrical Code Section 250.64, he addresses the protection of grounding electrode conductors and bonding jumpers. While it doesn't explicitly mandate bonding of short electrical metallic tubing sleeves, it does require that grounding electrode conductors be securely fastened to the surface on which they are carried and protected from physical damage. The use of an electrical metallic tubing sleeve is a common method of providing this protection. The question of whether to bond a short electrical metallic tubing sleeve often arises because of the general rule in the National Electrical Code Section 250.92. A3, which requires bonding of metallic raceways and enclosures containing service conductors. This rule aims to minimize voltage rise on these metallic parts during a fault and to provide a lower impedance path for fault current. Although grounding electrode conductors are not service conductors, the principle of providing a low impedance fault current path is equally important. Therefore, the industry best practice of bonding both ends of the electrical metallic tubing sleeve to the grounding electrode conductor is a reasonable and prudent approach. The method of bonding the electrical metallic tubing sleeve to the grounding electrode conductor is typically achieved using bonding jumpers. A bonding jumper is a short length of conductor used to connect two metallic parts together, ensuring electrical continuity. The size of the bonding jumper is determined by the size of the grounding electrode conductor. as specified in the National Electrical Code Table 250.102. C1. The bonding jumper must be securely attached to both the electrical metallic tubing sleeve and the grounding electrode conductor using appropriate connectors, such as bonding bushings or grounding clamps. These connectors must be listed for the purpose and installed in accordance with the manufacturer's instructions. In addition to improving the grounding path and enhancing safety, bonding the electrical metallic tubing sleeve can also help to reduce electrical noise. Electrical noise can be induced on the grounding electrode conductor by nearby circuits, particularly those carrying high-frequency currents. This noise can interfere with the operation of sensitive electronic equipment and can also create safety hazards. By bonding the electrical metallic tubing sleeve, you create a shield that helps to block electromagnetic interference and reduce the amount of noise in the grounding electrode conductor. It's also crucial to consider the material compatibility of the grounding electrode conductor, the electrical metallic tubing sleeve, and the bonding jumpers. Dissimilar metals can create galvanic corrosion, which can weaken the connection and increase the impedance of the grounding path. To prevent galvanic corrosion, it's important to use compatible materials or to use connectors that are specifically designed to prevent corrosion. For example, if the grounding electrode conductor is made of copper and the electrical metallic tubing sleeve is made of steel, you should use copper connectors that are listed for use with both copper and steel. The installation of the grounding electrode system should also comply with all applicable local codes and regulations. These codes may have additional requirements for the bonding of electrical metallic tubing sleeves or other metallic enclosures containing grounding electrode conductors. It's important to consult with a qualified electrical inspector to ensure that the installation meets all applicable requirements. Proper grounding and bonding are essential for the safe and reliable operation of electrical systems. By following industry best practices and complying with all applicable codes and regulations, you can ensure that the grounding system provides an effective path for fault current, minimizes electrical noise, and protects people and equipment from electrical hazards. Let's delve deeper into the specifics of grounding electrode conductors and their proper installation. Grounding electrode conductors are the critical link between an electrical system and the earth, providing a low impedance path for fault currents. The selection, sizing, and installation of these conductors are governed by the National Electrical Code, specifically Article 250. A thorough understanding of these requirements is essential for electrical professionals. The primary function of a grounding electrode conductor is to connect the system grounded conductor, typically the neutral, or the equipment grounding conductors to a grounding electrode. This electrode can take several forms, including ground rods, metal underground water pipes, concrete encased electrodes used for grounds, or ground rings. The choice of grounding electrode depends on site conditions and local code requirements. The size of the grounding electrode conductor is determined by the size of the service entrance conductors or, in the case of separately derived systems, the size of the derived phase conductors. The National Electrical Code Table 250.66 provides the minimum size requirements for grounding electrode conductors based on the size of the service or derived conductors. It's important to note that this table specifies the minimum size, and in some cases, a larger conductor may be required to ensure adequate fault current carrying capacity. When a grounding electrode conductor is installed, it must be protected from physical damage. This is often achieved by running the conductor through a rigid metal conduit, intermediate metal conduit, or electrical metallic tubing. As we've discussed, the National Electrical Code does not explicitly require bonding of short electrical metallic tubing sleeves used to protect grounding electrode conductors. However, the underlying principle of minimizing impedance in the grounding path and providing a safe path for fault current strongly suggests that bonding is a prudent measure. The impedance of a conductor is influenced by both its resistance and its reactance. Resistance is the opposition to current flow due to the material's inherent properties. Reactance, on the other hand, is the opposition to current flow due to the effects of inductance and capacitance. In the case of a grounding electrode conductor enclosed in a metallic raceway, inductive reactance can become a significant factor, especially under fault conditions where high currents are present. The alternating current flowing through the grounding electrode conductor creates a magnetic field that encircles the conductor. This magnetic field induces a voltage in the metallic raceway, which can cause current to flow in the raceway itself. If the raceway is not properly bonded, this induced current can create a circulating current that opposes the flow of fault current in the grounding electrode conductor, effectively increasing the impedance of the grounding path. By bonding both ends of the electrical metallic tubing sleeve to the grounding electrode conductor, you create a parallel path for fault current. This parallel path reduces the overall impedance of the grounding system and ensures a more effective path for fault current to flow back to the source. The bonding jumpers used to connect the electrical metallic tubing sleeve to the grounding electrode conductor must be properly sized and installed. The National Electrical Code Table 250.102 C1 provides guidance on the minimum size of bonding jumpers based on the size of the grounding electrode conductor. The bonding jumpers must be securely attached to both the electrical metallic tubing sleeve and the grounding electrode conductor using listed connectors. These connectors should be suitable for the materials being joined and should be installed in accordance with the manufacturer's instructions. In addition to the electrical considerations, it's also important to consider the mechanical aspects of the installation. The electrical metallic tubing sleeve should be securely supported and protected from physical damage. The grounding electrode conductor should be run in a straight and direct path, avoiding sharp bends or kinks that could increase impedance. The entire grounding electrode system should be inspected and tested to ensure that it meets all applicable code requirements and that it provides a low impedance path for fault current. Regular inspections and testing are essential to maintain the integrity of the grounding system over time. Corrosion, loose connections, and physical damage can all degrade the performance of the grounding system and compromise its ability to protect people and equipment from electrical hazards. In summary, while the National Electrical Code does not explicitly require bonding of short electrical metallic tubing sleeves used to protect grounding electrode conductors, industry best practices strongly recommend it. Bonding the sleeve provides numerous benefits, including a reduced impedance grounding path, improved safety, and reduced electrical noise. By following these best practices and complying with all applicable code requirements, you can ensure that the grounding system provides a safe and reliable path for fault current and protects people and equipment from electrical hazards. The topic of grounding and bonding is complex and multifaceted. It's essential for electrical professionals to stay up to date on the latest code requirements, industry best practices, and technological advancements in this field. Continuous learning and professional development are critical to ensuring the safety and reliability of electrical systems. Let's further expand on the practical aspects of implementing these bonding recommendations. When dealing with a 500 kc grounding electrode conductor, the selection of appropriate bonding jumpers and connectors becomes paramount. According to the National Electrical Code Table 250.102, C1, a 500 kc copper grounding electrode conductor would require a minimum 1/0 American wire gauge copper bonding jumper. This size is essential to handle the potential fault current that could flow through the grounding system. The choice of connectors is equally important. For connecting the 1/0 American wire gauge bonding jumper to the electrical metallic tubing sleeve, you should use a listed grounding bushing or grounding wedge connector. These connectors are designed to provide a secure and low impedance connection to the metal raceway. It is crucial to ensure that the connector is properly sized for the electrical metallic tubing and that it is installed according to the manufacturer's instructions. Over-tightening or under-tightening the connector can compromise the integrity of the connection and increase the risk of failure under fault conditions. For connecting the bonding jumper to the 500 kc grounding electrode conductor, you should use a compression-type connector that is specifically listed for use with large conductors. These connectors are designed to provide a reliable and gas-tight connection that can withstand the mechanical stresses and thermal cycling that may occur in the grounding system. It is essential to use a crimping tool that is specifically designed for the connector being used, and to follow the manufacturer's instructions for crimping the connector. An improper crimp can result in a high resistance connection that can overheat and fail under fault conditions. When installing the bonding jumpers, it is important to ensure that they are as short and direct as possible. Long or circuitous bonding jumpers can increase the impedance of the grounding path and reduce the effectiveness of the grounding system. The bonding jumpers should also be protected from physical damage. If they are exposed to mechanical stress or abrasion, they should be protected by conduit or other means. In addition to the bonding of the electrical metallic tubing sleeve, it is also important to ensure that all other metallic parts of the electrical system are properly bonded. This includes metal enclosures, raceways, and equipment frames. The purpose of bonding is to create a low impedance path for fault current to flow back to the source, allowing the overcurrent protection devices to quickly trip and clear the fault. Improper bonding can result in elevated voltage on metallic parts, which can create a shock hazard. The National Electrical Code Article 250 provides detailed requirements for bonding of electrical systems. It is essential to be familiar with these requirements and to follow them carefully when installing or maintaining electrical systems. Regular inspection and testing of the grounding and bonding system is also important. This can help to identify and correct any problems before they become a safety hazard. The testing should include visual inspection of the connections, as well as impedance testing to verify that the grounding path is low impedance. In conclusion, the bonding of electrical metallic tubing sleeves protecting grounding electrode conductors is a critical aspect of ensuring the safety and reliability of electrical systems. By following industry best practices and complying with all applicable code requirements, you can create a grounding system that provides a safe and effective path for fault current and protects people and equipment from electrical hazards.